talk about finding volume of solids using what's called known cross-sections. So previously we were finding two-dimensional surfaces, right? We were finding the area between curves as shown in the figure at the left, right? Finding the area between f of x and g of x. And now we're going to be moving into more three-dimensional uses of integrals. So finding the volume of a solid made using an area between two functions. So you can kind of see a Play-Doh model in the picture on the right, where you can see that there's a Play-Doh layer down like on the graph field, and there's those semicircles popping up. So you can kind of see that there's a solid figure being formed with a different volume. So to start finding volume of solids using calculus, we're going to be doing that by constructing a solid using the area between two functions as the base. So in the picture on the left, you can see that I've kind of shown you that this is going to be the area, this is going to be the base of our solid. And that's just the area between two curves, so something that you've been using calculus to find. And so then what we're going to do is we're going to be projecting different cross-sections, so different shapes, out of that base in order to create a three-dimensional object, which I have one picture there on the right, so that's using squares. And I'm just going to quick kind of pop into this. So this is that same applet that I have a picture of there, so you can kind of see that we have that same area that I had highlighted in blue on my screen before, and now you can kind of see if I rotate this that we have these squares that are forming a solid, right? And there's a lot of space between those squares, so as I increase the number of squares that I'm projecting out of that area, right, so right now I'm at n is 37, there's 37 squares there. If I take it all the way up as far as I can, I get 100 of them. You can see that we have a very solid object. You can kind of see the curves that are made up by those squares. But if you sliced it, like if you had a knife and you were like slicing this like a cake, every slice would form a square. I'm going to take this down a little bit so we can see the space and see actually the cross sections again. Right, so we can do this with different shapes. So that's a square. Oftentimes we'll also be asked maybe with triangles. So if we do this with triangles, we can see now that there's a triangle in each of those sections. And again, if we take more and more triangles, we'll see a slightly different solid appearing. Again, taking that all the way up to 100 triangles. Now it's like kind of coming up. It almost looks like the back of like an animal or something with like a curved spine like that, like maybe the back of a dinosaur, I don't know. But I can put the squares on top of it so you can see the squares look like that, but if I change it to equal out all the triangles, we get this. Again, I'm going to take this down so we can see the individual shapes again. And we also can do this with semicircles. You can do this with any geometric shape, any two-dimensional geometric shape. So you can see there we have our solid forming with semicircles. Again, I'm going to take that all the way up to 100. And now you can see a totally different solid appearing. It's nice and smooth on the top. Maybe kind of looks like a pasta noodle to me, especially with the ridging there. Right, so we have all of that. So I can put that on. So now you can see the triangles kind of appearing at the top. It looks like the back of a fish now, right, with the fin on top. And then with the squares, it gets even bigger, and we can't even see the other shape. So just going back to the iPad now. Okay, so we're going to be doing that today. So some useful volume formulas that you might want to know is you might want to just refresh yourself on how do you find the area of each of these shapes, right? Because we're going to be building the volume by adding up all of these areas, right? That's all volume really is if you take a thin slice, you get this two-dimensional object, and if you add the area of all of those up, you're going to get this three-dimensional object, right? So a square we know, right? This should be the word area because we're going to use those area formulas to find our volumes, right? So area is just side squared, where S is the side length. Right, a rectangle, right? We know our area is just length times width. I'm just going to write it out in words. Right, a semicircle, right? So that's just half of a circle, so that's going to be 1/2 pi r squared. For this one, you want to be careful that r is the radius, right? And the radius is going to be from the center point of the curve, right? So you want to be careful about that. And then triangle, we know that is 1/2 the height times the base in general. Right, and how you find those different things is going to be based off of the type of triangle that they give you. So we're going to go through a couple of examples using these different kinds of shapes. The first few examples we're going to do is non-calculator. I'm just going to go through the whole process, and then we're going to kind of do an example where it's a little bit more involved, and we'll just do it with the calculator after we set up the integral. So for our first example, we want to find the volume of the solid whose base is the area bounded by the graphs of negative 2x plus 3 and x squared, and whose cross sections are going to be perpendicular to the x-axis. So that tells us that the cross sections land on the x-axis. This tells us that we have a dx integral. And we're going to do this, would help if I could spell integral as a math teacher. There we go. We're going to do this 3 different times with 3 different cross sections. So the first thing we probably want to know is what the bounds on this area are. So we're going to set our 2 equations equal to start. And I'm going to move everything from the left to the right so I get a nice little quadratic here. And it's nice that it factors, so we get x plus 3 times x minus 1. So we get that x can be negative 3 or positive 1. So I'm going to just sketch a quick little graph. So negative 3 to positive 1. I'm going to move my little xy axis over here. Okay, so I got negative 3, 1, 2, 3, and then 1. So if I plug negative 3 into x squared, I get 9. So I got to go 1, 2, 3, 4, 5, 6, 7, 8, 9. If I plug into 1, I'm going to get 1. Okay, so if I focus on graphing my parabola first, because that's pretty easy to graph, I know I'm going to be down here, here. 2 squared is 1, 2, 3, 4. Okay, so we've got our parabola curve, and then if I graph negative 2x plus 3, I have a y-intercept of 3. Right, I know I'm going to hit those endpoints there, and it's a straight line. Okay, if I plug in negative 1, though, I'm going to get 2 plus 3 is 5. Right, and then if I go up another 2, I'm going to get 7. Right, so it looks like my points are just a little bit off because graphing without a grid. Right, so we've got this area here. This is going to be the area that we are projecting our different shapes off of. Ignore my poor coloring skills here. Okay, so the first thing we want to do is we want to project squares out of this. So when we project these squares, I actually have a thing on Desmos up here. We're just going to quick look at that. So here we have, right, you can see I've graphed negative 2x plus 3 and x squared. We are doing squares, so we have a shape of 4. Hang on, I just want to take the number of cross sections that we have down. Okay, so you can kind of see if I can rotate this properly, right? We have that same area that we just drew, and we are now projecting squares out of the base, right? So we can kind of see that the base of the square is that height between the 2 functions. And as I increase the number of squares here, we can see that solid really forming. It's a little harder to see on Desmos than it was on the GeoGebra applet that I had up before, but we can see that that's a solid shape now. Let's just take that down, make it a little easier to see all of the different squares there, right? So you don't have to be able to like have that up or anything in order to visualize this. You just want to know, okay, like I've got squares coming out of the base, so I know that my height, right, my side here is going to come out of there, and then I can kind of pretend to be projecting them out into 3-dimensional space. Right, so I know that S is going to be the height of my square, and that is going to be, right, the difference between those 2 functions is the height. So my top function is negative 2x plus 3, and then I'm going to subtract my bottom function. So I know to find the area of 1 square then, I'm going to take that negative 2x plus 3 minus x squared, and I'm going to square it. So to find the volume by a cross-section, right, you find the area of one generalized square, and then to find the volume of the shape, we're going to integrate from the limits on the on the area. So that's going to be negative 3 to 1, and then I'm just going to rearrange this to make me a little happier. Right, so we're just going to integrate that area formula. So, right, I'm just going to quick kind of think about multiplying this just going to write it out again over there so that way I can kind of visualize how I'm going to square that out, because that's just going to be the easiest way to do this. U substitution is not going to work here. So if I FOIL, okay, that's going to be 4x squared minus 6x plus 2x cubed. Okay, and then I got minus 6x again. Here, you know what we're going to do? We are going to just click that down. Okay, right, so that was 4x squared minus 6x, and then I had positive 2x cubed. So I'm going to throw that in the front. I like to have my terms in the correct order. Okay, and then if I distribute my 3, I'm going to get another negative 6x plus 9 minus 3x squared. Then if I distribute my x squared, I'm going to get, let's see, we got positive 2x cubed again, minus 3x squared, and then plus x to the 4th. All right, so that's really messy, but that's okay. Delete that. What happens when maybe you don't plan out your space appropriately? Well, this is totally fine. Okay, so we got, this is x to the 4th plus 4x cubed. That's minus 6 plus 4, so minus 2x squared minus 12x plus 9. Really hoping I did that correctly, did my algebra right. Throw that in my integral. Maybe I was silly to say this was a non-calculator question, but that's okay. Throw some more page room in there. Okay, so we got 1/5 x to the 5th plus x to the 4th minus 2/3 x cubed minus 6x squared plus 9x. We're going to evaluate that from -3 to 1. Okay, so 1 is pretty easy, right? So we got 1/5 plus 1 minus 2/3 minus 6 plus 9 minus, okay. Whew, I was definitely silly to do this without a calculator. Okay. Whatever. We're going to say, we're just going to keep doing it for this one. Maybe we'll throw a calculator on there for the next one. We'll see. 3 to the 5th is 243, so that's negative 243 over 5 plus 81, and that's going to be positive 2/3 times 3 cubed is 27 minus 6 times 9, so 54 minus 27. Okay. Let's see, we got 1/5 minus 2/3. 1 plus 9 is 10, minus 6, that's plus 4. Minus, okay, let's see, 54 and 27. Right, that's 11. Okay, that's 81. So these are all going to cancel out. Wonderful. 2/3 times 27. Okay, 27 over 3 is 9. That's going to be plus 18. So I'm actually going to cancel out that. So we're going to get plus 243 fifths minus 18. Okay, so that's going to be 244 fifths minus 2/3 minus 14. Okay, let's make a common denominator then. Okay, 244 times 3, it's going to be 12 carry the 1, it's going to be 13 carry the 1, 732 minus 10 minus 14 times 15, that's 20, carry that. That is going to be 210 then, right, all over 15. Okay, so let's see, that's 732 minus 220, so that's 215. Okay, that was a lot harder than it needed to be and a lot longer of a process. We'll use a calculator probably on the next couple just to speed this up. Okay, so now we're going to do the same region. I'm going to actually go back and copy my graph over so we can kind of see that. Now we want to do area of the rectangles where rectangle is, height is twice the base. So let's see if I can get that. Okay, we're just going to ignore that extra pink line in there, that's fine. Okay, so right? The base of that rectangle, right, is going to be that side S. So base is going to be that negative 2x plus 3 minus x squared, right, height between the functions. So now the height is going to be twice that. So we've got 2 times that. So then the area is going to be 2 times negative 2x plus 3 minus x squared, all squared. So when we go to find the volume, just notice I spelled area wrong. There we go. We're just going to do the integral from negative 3 to 1 of that area expression. And since we've already squared that out, I'm going to go ahead and find my calculator. And we're going to go over here, and let's see, let's go to Math 9 for integral. We're going to do negative 3 to 1 of 2. Sorry for the background noise, that was Mr. Baxter coming in. Negative 2x plus 3 minus x squared. Go outside of our parentheses and square that. There's my square. No! There we go. And not di, we're going to do dx. That wouldn't make sense. Okay. So we get that gnarly thing. If you wanted to make it a fraction, write math, enter, enter. Right, we could say that this is 1024 over 15, which is approximately 68.267. Right, we'll ignore the no calculator thing, whatever. We ain't got time for that. Okay, so now we're going to do semicircles. So again, I'm going to copy this over here. I'm going to actually take all of this out. Okay, so now we have a semicircle, right? So the base of our semicircle is going to be right here. So that's the diameter. So the diameter, I'm going to ignore this, right, is going to be that negative 2x plus 3 minus x squared quantity. But to find the area of a semicircle, right, you need to know the radius. So the radius is going to equal half of that. And then the area of a semicircle is 1/2, I don't know why I made that a t, 1/2 pi times the radius squared. So if I want to simplify this just a little bit, if I square that 1/2, I get 1/4, multiply that by the half that's on the outside. So now my volume is going to be negative 3 to 1 integral of that 1/8 pi times negative 2x plus 3 minus x squared. Oh, I just realized I didn't switch it back so you could see it. I'm sorry. You can't watch what I'm doing. There we go. My bad. I forget that I'm not just on the iPad. I'm using my laptop for this too. My bad for that. Okay, so now you can kind of see all my calculations, right? We have that that would be like the center point of our semicircle there, so that would be our radius. Okay, so now I'm going to move this, and I'm just going to actually scroll up and copy down this integral because it's almost the same thing. And then I'm just going to make this a fraction in the front, and I want that to be pi over 8. And then I'm just going to delete out the 2, and there we go. So that would be approximately 13.401. If you wanted to know what that was as a more exact answer, like with a pi in the answer, if you do the same thing but make the pi a 1. Okay, there we go. And then make it a fraction answer. So our exact answer here would be 64 over 15 pi, which is approximately that 13.404 answer. And again, you guys can't see that because I didn't move the screen up. There we go. Right, so that's how you can get both the exact and the approximate using your calculator, right? You just take the pi out. Okay, so we're going to do one more just to kind of switch it up. So definitely going to use a calculator for this just to speed it up. So Now we have the base of a solid is bounded by x squared, y equals 0, and x equaling 2. So let's just quick sketch that. Okay, so if I have x equaling 2, that's here. Right, y equaling 0 is the x-axis. And then if I graph, right, x squared, I'm going to need to go up to 4. So 1, 2, 3, 4, 0, 1, and then 4 up here, right? Just nice little parabola. So we have this area right here that we're finding. That's going to be the base of our solid. And now we're going to take cross sections that are perpendicular to the y-axis. So that tells us that we're going to have a dy integral. And we have isosceles right triangles where one of the legs is lying in the base of the solid. Okay, so if I draw a couple here, right, to find the length of that line, right, if this is y equals x squared, that means that y squared, that means that the square root of y is equal to x. That's the same curve there. And then, right, this is just x equaling 2. So to find the distance between those, right, our lines there, it's just going to be the line, so 2 minus the curve, so the square root of y. So that's going to be the length of that line. So now if we think about an isosceles right triangle, so we have equal sides there, and it says one of the legs is lying in the base. So that means, sure, that's a fine color. We got 2 minus the square root of y here, but since it's isosceles, this is also 2 minus the square root of y. So if I want to go ahead and find the area of one of those triangles, it's going to be 1/2 the base times the height. So in this case, the height and the base are the same, so I can make that 1/2 times 2 minus the square root of y squared. You could easily FOIL that out and do this one by hand. We're just not going to. So then for the volume, I want to remember that we're going to have a dy integral, which is why everything is in terms of y's. So when we're going to find out the limits of our integration, right, the bottom y coordinate is 0 and the top y coordinate is 4. So we're going to go from 0 to 4. And then we're just going to go and type that in on our graphing calculator. So again, math 9, we're going from 0 to 4. And then we had, what was it, 1/2, so 0.5 times 2 minus the square root. It says y, but I'm going to use x just for ease of typing. Squaring that quantity, I used an x, whoops, what was that? Go away. Now we're going to scroll all the way through because I pressed the wrong button. Okay, hit x. There we go. We can get our decimal approximation. We can also make that a fraction, which this is too bad for my calculator to do, but you can see that it's like 1.33 basically. There's a little bit of error probably there on the end with the calculator approximation. So this is probably 4/3 is the answer. So we're just going to write the decimal there, 1.333, just to be on the safe side.